Alright, we're going to begin section 15.6 in this video, which is integrals over oriented surfaces. Oops. And for us, you can just think of when we're having oriented surface, we only have to orient our surface because we already learned how to do a surface integral. We only have to orient the surface if we're doing a surface integral of a vector function or a vector field. So we only know how to do surface integrals of scalar functions so far. So this section could be entitled surface integrals of vector fields or vector functions instead of integrals over oriented surfaces. But they just specify the oriented surfaces because when you do a surface integral of a vector field, you have to have some kind of orientation on your surface, which we'll talk about in this section what that means. So if the vector field F is a continuous vector field, defined on an oriented surface S, with a unit normal vector that we'll call N, then the surface integral of F over S is, so the surface integral over S of F dot N and then D capital S. Now, this is just a notational thing right here. So that notation says that we are evaluating the surface integral, or you may sometimes hear it called flux. So surface integral of F over S. And this is of a vector field, not a scalar function. So this, we normally don't use this notation. Is not a computational thing. So you're not going to take F and dot it with the unit normal vector. Now it can be done, but it's a rare instance that we do that. So in practice, what we're actually going to use is we're going to use, if this is equal to plus or minus the double integral over some region R, and I'll specify what that region R is, of your vector field F. Then you take that vector field F and you substitute it in your parameterization for your surface F of R of UV, and then you dot that with R sub U cross R sub V and then dA. So this actually is a normal vector, but it doesn't tend to be a unit normal vector though. So these do look, this right hand side of course looks the same as that, and they are equal to one another, but this is more of a notational thing than an in practice thing. So the reason I stress that is because you want to be careful to not just say, okay, well, I'm going to pick any old normal vector, unit normal vector for my surface, and I'm going to dot that with my vector field. And when you notice the way you compute this normal vector right here has to come from that parameterization right there. So that's why you want to be careful, because your your surface is going to have infinitely many normal vectors, but you have to make sure that you computed that normal vector based upon whatever parameterization that you used. You can't, if this doesn't match that, your answer is going to come out wrong in your problem. So you don't really want to try to use this approach to compute. That's just a notational thing. Always use this over here to compute. All right, and so this is our shorthand notation, and I'll talk about how we determine the plus or minus as well. So writing this all the way out. So this is plus or minus the double integral over region R of f of x of uv, comma, y of uv, comma, z of uv. You dot that with r sub u cross r sub v and integrate that. Now we'll specify what the capital R and the lowercase r are, where r of uv equals x of uv, comma, y of uv, comma, z of uv. For uv in some region R is a parameterization of S and R sub U cross R sub V points in the direction of what your unit normal vector in. So this is what's going to determine if these two things coincide. Then you're just going to use the plus of the two, the plus or minus. If R sub U cross R sub V points in the opposite direction of the unit vector that you were given, you use the minus. So in actuality, my explanation right this down here, which says they do point in the same direction, really is just the plus integral. If it so happens they don't point in the same direction, that when you take this cross product, it doesn't point in the direction, and this direction in will be given in the problem. It will say outward orientation or upward or whatever the case may be. That will be given in the problem. If you take this cross product and that normal vector doesn't point in the same direction as this, then use a minus sign. Now, how do we know which direction this points in? Because this is going to be a function of u and v. You just take a point, u comma v, and plug it in there, and then you can see which direction it points. Now, what we haven't talked about is orientation of a surface. So and it's not going to be as you'll quickly realize, it is not going to be a concrete definition. It's going to be more of an intuitive thing. All right, so let's sketch a set of coordinate axes, or actually two sets of coordinate axes. And while this approach is not concrete by any stretch of the imagination, it is probably the most widespread explanation amongst Calculus 3 textbooks as to how to understand orienting a surface. So it's not something that I made up. And we're going to sketch the exact same surface on both of these sets of coordinate axes. Or try to, at least. So you just sketch some surface. Doesn't really matter what it looks like, but try to keep it simple. All right, so there's our surface. Now this surface, and I just put some little curves on here to indicate that this is not a curve, it's actually a surface. Now, any surface that we have, so we have some normal vectors on this surface. So sketch a few of those. So these are our unit normal vectors. So this surface, a question would read with upward orientation, where now this point right here is not directly upward, but in the general direction is upward orientation. So what we do and the way that this is explained in several textbooks is that what you do is any surface is going to have an inherent boundary curve on that surface. So we have these normal vectors that are pointing upward. So what you're going to do is whenever you have, and you won't have to do this in practice, but just so you understand how this is working, because you're not going to have to sketch your surfaces. So what you're going to do is you are going to sketch yourself a little stick figure on the boundary curve, and the stick figure's head has to always point in the same direction as the normal vectors. So now in this picture over here, we're going to sketch our normal vectors in the downward direction. So we'll just sketch a couple of those. And now that means my stick figure here, the head of the stick figure has to go in that downward direction. So now, whenever your stick figure is on the boundary curve of your surface, now we have to determine which way that stick figure is going to walk. Now, the way that that is explained is that that stick figure should always be walking walking with the surface of the surface to his or her left at all times. So in this scenario, I have no choice but the stick figure's head has to be pointing in the direction of the normal vector. Now, the stick figure is supposed to either walk this way or this way. Now, just imagine you were walking on this surface. Which way would you walk to ensure that the surface is on your left at all times, given your head is pointing in that direction? You would have to walk in this direction. So now we have the surface orientation, which is these normal vectors pointing upward, induce an orientation on this boundary curve. And that's going to be important to us. A little more so in the next section than it will in this section, but it still nonetheless will be important to us. So that boundary curve has to have the induced orientation from whatever the surface orientation is. And then same thing here. So these normal vectors are pointing down, so you kind of would have to imagine yourself being upside down. And now you need to walk in a direction to ensure that the surface itself is on your left at all times. Now, in this scenario, because we have the same picture and we just flipped our normal vectors, we know for sure it's going to go in the opposite direction. But do your best to try to visualize that, because it will be useful. And we're going to do some problems that actually, there's some problems in this section, so we'll do some problems that kind of assist with that as well. So now for us in practice, what you're going to see in the problem is you're going to see that your normal vector or whatever points upward. It'll say that the unit normal vector points upward. Then you'll take this cross product from whatever parameterization you choose, and you'll see, okay, I plug in a point UV to this cross product. Does it also point upward? And if it does, then you don't need to do anything which is with regards to changing the sign. If you take the cross product of this and it happens to point downward, even though you were told your normal vector points upward, you don't have to do anything with these pictures or any curve or anything like that. You just put a negative sign in front of your answer, and that'll address that issue for you. You don't need to retake your cross product. Nothing needs to be done. Just slap a negative sign in front of your answer, and that'll do the trick for you. So I'll just put that down in writing so we know. The orientation of your surface can easily be checked. Actually, I should have said the orientation of your parameterization, really. Let's say your parameterization. Your surface parameterization, because you're not checking the orientation of the surface that's given to you. You're checking, did your parameterization, is it oriented the same way that the surface was given to you in the problem? The orientation of your surface parameterization can easily be checked. By plugging a test point u comma v into r sub u cross r sub v to ensure it points in the correct direction. All right. And the reason just putting a negative sign in front of your integral fixes it is because remember that r sub u cross r sub v, if you were to take the cross product in the other direction, all that does is just change the sign, but it makes your normal vector point in the opposite direction. So instead of you trying to redo your cross product, because all it's going to do is give you the same thing but times a negative sign, you just take that negative sign you will get from redoing your cross product and you just put it out in front of the integral. All right, so I'll stop this video here and then we'll continue with 15.6 in our next video.